So let's take a look at curvilinear motion. This is the general 2D motion, which could be a straight line or could be moving along some sort of curve. It's described by a vector that changes in time. So let's call that vector r. It's bold since it's a vector, or we draw it with an arrow over it, and that vector can change both its length and its direction over time. Velocity is always going to be tangential to the motion, right? So if the particle is moving along this blue line, velocity is always going to be perpendicular to that line at each point. So the velocity is still, just like last time, defined as the time derivative of position, and both of these are vectors. Acceleration, once again, defined as the time derivative of velocity. Nothing has changed there. Both of them are vectors. The direction of the acceleration, however, is perpendicular to or tangential to the velocity curve. If you were to plot the velocity curve as in this pink line, then the acceleration would always be tangential to that. That doesn't mean that it's tangential to the position curve, right? So the position curve, the acceleration could be at any angle relative to the position curve. We're going to start by looking at rectangular coordinates. These are the coordinates we're used to seeing, the x, y, and z. Next time we're going to be looking at two other coordinate systems. But for today we'll stick with rectangular coordinates. So a general position r, the vector r, can be written as some distance in the x, I hat, some distance in the y, j hat, plus some distance in the z, k hat. It's a general 3D vector notation for position. The velocity then is the time derivative of r. Since I hat, j hat, and k hat are unit vectors, they have a fixed direction and they have a fixed length, which means the derivative of them is 0. So to take the time derivative of r, we just get the time derivative of the x part, I hat, time derivative of the y part, j hat, time derivative of the z part, k hat. And we can also write this as the x part of the velocity, the y part of the velocity, the z part of the velocity. Same idea with acceleration. All right, we're going to take another time derivative, the time derivative of the velocity, so we at x double dot, second time derivative of x in the I hat direction, y double dot in the j hat, z double dot in the k hat. Now if you think back to the general equations that we had last time, we had 3 of them. One was that the velocity is the time derivative of the position, the acceleration is the time derivative of the velocity, and then we had the combined version that was a dx equals v dv. Right? Those 3 equations are going to hold for all 3 directions, so we are up to 9 equations now. They're written here in terms of x, but you can write the same equations for y and z as well. So these are vectors. So let's take a look then at some quick reminders about vectors. If you want more information about vectors, go back to your statics notes or take a look at Appendix B in the Hibbler text. So a general vector can be written as an x part in the I hat direction, y part in the j hat direction, and a z part in a k hat direction. Alright, I hat, j hat, and k hat are unit vectors in the x, y, and z direction. They have a magnitude of 1, that's constant, and they have a constant direction along the x-axis, the y-axis, or the z-axis. A magnitude of a vector is given by the square root of the sum of the squares of its components. If we want the direction of a vector, we're being really asked for a unit vector in that direction, right? So the unit vector in the direction of A is given by the x part of the vector divided by its magnitude in the I hat, the y part of the vector divided by its magnitude in the j hat, and the z part of the vector divided by its magnitude in the k hat. You'll probably remember from statics we did a lot of vector addition. There's 2 ways to do this. You can do tail to tip. So you line up all your vectors tail to tip, and then you connect the tail of the first one to the tip of the last one, and then use geometry to find the length of that and direction of that vector. Or you write them out as I hat, j hat, and k hat components and just add up the i's, add up the j's, add up the k's. We also saw 3D vectors in statics. We'll see a little bit of 3D vectors in dynamics, but we'll primarily be focused on 2D vectors in dynamics. So just as a quick reminder, if we're given alpha, beta, and gamma, where alpha is the angle from the x-axis to the vector, beta is the angle from the y-axis to the vector, gamma is from z to the vector, then we can write the x part, the y part, and the z part as simply a, the magnitude, cosine alpha, cosine beta, or cosine gamma. There was another version that we saw in statics that we won't be dealing with here that had theta, phi, and gamma as our angles. So let's take a look at an example. This is a time-dependent example, which means that our position vectors are written in terms of time, t. So we have two particles. We're given vector notation for their positions at any given time, and we're being asked when they will collide. So what time will they collide, and what are their speeds just before they collide? So to figure out when they collide, we recognize that if two particles collide, then their x position and their y position at that time must be the same. Alright, so if we look at the x direction first, let's look at the s. So that's the I hat part of each one. We've got 3t for particle A is going to equal 3 times t squared minus 2t plus 2 for particle B. So then we also have the y direction, right? So looking at the y's, that's the j hat parts. So we've got 9t times 2 minus t is going to equal 3 times t minus 2. And both of these equations have to be satisfied if these particles are going to collide. It's very possible that they wouldn't collide, but since we're being asked for it, we're going to assume that they will. So let's see. Let's solve each of these equations for time. So these are a quadratic equation. Let's see, the 3's cancel, there's one on each side. We move this t over, we get 0 is equal to t squared minus 3t plus 2. Standard quadratic equation, we can solve it. T is going to be either 1 or 2. Two options, two solutions to any quadratic equation. Alright, solve the other side. We get 18t minus 9t is equal to 3t minus 6. Move things over, we get 0 is equal to 9t squared minus 15t minus 6. And we solve that as a quadratic equation. We get t is equal to either negative 1/3 or 2. Now obviously negative 1/3 is not an option. Time cannot be negative. So we'll get rid of that, and we notice that there is a time that satisfies both of these equations, t equal to 2. So we're going to get a collision at t equal to 2. So that's part A. Part B asks us for information about the velocities, or not the velocities, the speeds of each of these particles right before they collide, so at t equal to 2. So we're given position, we need to find velocity, and from velocity, the magnitude of velocity is going to be speed. So we start with RA, which is equal to 3t I hat plus 9t. Let me actually multiply this out so the derivative is easier. 18t minus 9t squared j hat. Let's take the derivative of this. We're going to get VA. Derivative of 3t is 3. Derivative of 18t is 18 minus derivative of 9t squared is 18t j hat. So now we have to plug in t is equal to 2, which is the time we're interested in. We get the velocity of A is equal to 3 I hat minus All right, we plug in 2 here, we get minus 18j hat. All right, now to find the speed, that's the magnitude of the velocity. So we're going to take the square root of 3 squared plus 18 squared. It's technically the square root of 3 squared plus negative 18 squared, but the negative 18 squared is the same as positive 18 squared. And this is 18.3 if you look it up. And the units would be meters per second, since we're working in meters. All right, do the same thing for RB. RB is multiplied out 3t squared minus 6t plus 6 I hat. That's the first part, plus 3t minus 6 j hat. All right, let's take the derivative of that. We get 6t minus 6 I hat plus 3 j hat. Plug in t equal to 2. Get 12 minus 6, so 6. Oh, hold on. Alright, VB, still a vector, is equal to 6i hat plus 3j hat at the time we're interested in. So the speed, VB, is the magnitude of this, 6 squared plus 3 squared. And you plug that into your calculator, you should get 6.7 meters per second. So we found the time that the collision occurred and the velocities of the two right before that collision. We could also find the accelerations just by taking another time derivative. Now let's take a look at an example where the expression, the path that it's following, is given to us in terms of position instead of time. All right, so in our case, we have a van. It's going over a hill, and we're given the curvature of that hill. We're told that y is equal to this negative 1.5 e to the negative 3x squared plus 15. And we need to figure out, well, we're told the speedometer on the car, right? So the speed that the car is traveling is 75 feet per second, and it's constant, so there's no acceleration in that direction. We're supposed to figure out the x and y components of the velocity and the acceleration when we're at x equal to 50 feet. So we will start by using this 75, right? So this is the speed. The speed is equal to the square root of the x part of the velocity plus the y part of the velocity. Those are the two things we're trying to find, and that is going to equal 75. All right, so this is one equation. We've got two variables we're trying to find. Now we need the other equation. Well, we're given a position, right? We're given the y part of the position as negative 1.5 e negative 3x squared plus 15. So let's take the time derivative of y. That would give us vy, right? So vy is equal to y dot, time derivative. So this is x. X is a function of time. So we need to use the chain rule here in order to find the time derivative. So we have negative 1.5 e negative 3. That sits out front. It's a constant. What is the time derivative of x squared? Well, the outer derivative of x squared is 2x. The inner time derivative of the x squared is x dot. And the time derivative of 15 is 0. All right, so what we've now figured out how to do is write Vy in terms of 1.5 e negative 3 times 2x Vx. But we know what x is in this situation, right? X is given as 50 feet. So Vy is going to be, if we plug in 50 for x and multiply it out, negative 0.15 Vx. So this is our first equation. This is our second equation. Two equations, two unknowns, right? We can solve that, or Wolfram Alpha can solve that, or something, or your calculator can solve that. And we end up getting that Vx is equal to negative 74.17 feet per second, and Vy is equal to 11.13 feet per second. All right, this negative sign came from the fact that if we look at this, if we draw the velocity of the car, all right, it's tangential to the curve, its x component should be negative and its y component should be positive. Knowing this, we can actually figure out what that direction is. All right, so what is this angle? Theta. That's going to be important in figuring out the acceleration. So let's do that now. All right, well, we've got, that's our v, which should be 75. We know its magnitude. All right, so we've got this part, which is 74.17, and we've got that part, which is 11.13. So to find the angle, this is theta, we get theta arctangent, right? Opposite over adjacent is the tangent. So the tangent of theta is opposite, 11.13, over adjacent, 74.17. So theta is equal to, let's see here, I had it figured out at some point, 8.53 degrees. All right, so we've figured out the first part of this. We found the velocities. Now we need to figure out the accelerations. So when we did the velocities, we knew that there was that 75 was the magnitude of the speed. We do know something about the magnitude of the acceleration as well. The magnitude of the acceleration is going to be 0. The direction of that acceleration, that's 0, is going to be the same as the direction of the speed, right? Since that's the direction that the 75 feet per second is constant in. So we then know that the acceleration in that direction at theta 8.53 is going to be 0. So what we need to do is any vector can be written as components of two perpendicular vectors. We want to write A in this direction. So this is, we want to write the acceleration in this direction in terms of AX and AY. Alright, so we don't know right now what AX and AY are, but I could draw them. I'm just going to draw them in the positive directions. That's AX. Here's AY. Now AX and AY, since they're vectors, have two components. Well, they have a whole bunch of pairs of two components. We want to pick the pairs of two components where one of those components is parallel to this direction and one of those components is perpendicular to those two directions. So we've got, here's the parallel, and then this one is the perpendicular, right? And this is theta. So if that's true, then this side, right, that's the part that's A, that side is going to be, let's see, the AX is the hypotenuse of this triangle, right? Here's the right angle. So this side is going to be hypotenuse times cosine of theta, because it's adjacent. Alright, we do the same thing with the AY. All right, there's our triangle. Let's talk a little bit about where theta is. Theta is, if we extend this out horizontally, this is theta, right? According to this diagram, because that's with the horizontal. So if this is theta, this is a right angle, then this is 90 minus theta, which would make this theta. Right? Okay. So now this side is the hypotenuse times the sine of theta, right? Because it's opposite the angle. Alright, so now we can write A in this direction, right? That's this part plus this part. Now let's look at directions. This one is going to be going this way. Whoops, tail to tip tells us this goes this way. And this one's going to be going that way. Alright, so they're in opposite directions. So A is going to be, if we drew A positive that way, then AY is going to be positive and AX is going to be negative. So we've got A is going to equal AX negative, so negative AX cosine of theta plus AY sine of theta, and we said in this direction, right, which is parallel to the velocity, the acceleration is 0 because the speed is a constant. Alright, so that is our first equation. And we know some information, we know what theta is the 8.53. So that's equation number 1. Equation number 2, just like equation number 2 over here in velocities, is taking the time derivative of this y double dot, right? So y double dot is y, right? It's the y component of the acceleration is y double dot. And we look at this expression and take the time derivative of it. Constant term just comes out front, e negative 3. And the time derivative of 2x, x dot. So, time derivative of the first part is 2x dot times the second plus time derivative, or plus the first times time derivative of the second. So there's 2 dots on that one. Alright, that's just the product rule for taking derivatives. And we know what x dot is because we found it, right? Because x dot, so x dot is equal to v, which is negative 74.17. And we know what x is, because that was given in the problem, is 50. So we can plug those two in and we get our second equation, which says that AY is negative 1.5 e negative 3, oops, e negative 3, 2 times negative 74.17 times squared, there's 2 of those, plus 2 times 50 times AX. So we have an expression for AY in terms of AX, and we have another expression of AX and AY is equal to 0. So 2 equations, 2 unknowns. We can solve that, and we will get AX equal to 2.42. In that units are feet per second squared in that direction. And AY is equal to 16.1 feet per second squared downwards. So in review of the problem, right, we used 2 different expressions each time. The first was information about the speed or the magnitude of the vector. And the second was the time derivative of this, of the given expression. And we use chain rule, so the key is to remember to use chain rule when you're doing these derivatives. And then we did the same approach for the acceleration. We just took the time derivative of the velocity, and we used information about the acceleration in a given direction. We knew that since the velocity, the speed was a constant, then the acceleration in the direction of the velocity would be 0. We ended up with 2 equations and 2 unknowns in each case, and we used our calculators to solve those.